So we have about 3 other problems to do out of section 3. And section 3 is talking about ratios. We talked about how to manipulate ratios to solve for the variable of interest. So we're going to do that in all of these cases. So the first case is just basically looking at a map and scaling it, scaling from the actual distance to the distance on the map. And you could come up with a scale and you could apply the scale, but you don't actually need to know what the scale factor is. You can just set up the appropriate ratios where you'll know there's 4 parts of a ratio. There's 2 of a proportion. There's 2 ratios, there's the numerator and the denominator of both sides. So that's 4 things. And if you give 3 out of the 4, you can figure out the 4th part. Now there's 2 ways you can do this. One is you can have the ratios involve the same units, or you can have the ratio involve different units but the same instance. So in this case, one instance is Tokyo, and that corresponds to 11 inches. And then we have Cairo, actually from Mexico City to Cairo is 7,700 miles. So what we're trying to do is figure out what is the corresponding distance on the map, the length on the map. So the 2 ways we would do it, if we did it based on units, we'd say 7,700 miles is to 3,300 miles as, and then you've got another ratio. You have another ratio, and you just have to make sure that what we have up here matches the corresponding numerator on the other side. So this corresponds to what we're trying to figure out, so we'll make that x. And for 3,300 miles, the corresponding part is 11 inches. The other way of looking at it is you could take, let's say, 11 inches, and instead of matching it up with the thing that involves inches is to match it up with the instance that we're talking about. So the thing that matches 11 inches is the distance from Singapore to Tokyo, which is 3,300 miles. And then the other side, again, is a ratio. In this case, what we're going to do is, since we have inches and miles here, we have to have inches and miles there. So here we have the unknown inches, and we have the known miles. And both of these ultimately will give you the same answer. So what we were saying was, rather than cross-multiplying and then dividing, what we can do is we can just take this term, which is in the denominator, and we can put it on the other side, and that means we move it to the numerator because that's what the rule is. When you have ratios, you can just move things around from one side to the other, and you just have to change them from the, in this case, from the denominator to the numerator on the other side. And the same way over here, if I want to solve for x, I've already got 11 inches over 3,300 miles. I want to get this to the other side, so it's in the denominator. So I'll move it to the numerator. So I'll have 11 inches divided by 3,300 miles times 7,700 miles. And you can see I have the same numbers. I have 11, 7,700 in the numerator, and 3,300 in the denominator, and then you can just do the multiplication. And we get the same answer on both sides because of the same numbers. 7,700 times 11 divided by 3,300 is 25.66. And if you look at the units, you'll notice the units for miles cancel out as well as here. So the final units on the answer have to be inches to be correct. And you'll get the same number over here, 25.66 inches. Now you could, yes, Eli. What's that? Yeah, so you want to go and do that? Oh, you want to just see what it looks like? Okay. Yeah, you got a memory stick or something? Yeah. I'll do that. Let me just stop the recording. Now you can rest. You can be confident that it's going to work out. Yeah. Okay. So now the other thing you could do is you could come up with a scale. You know, so many inches equals so many miles, and you could apply that scale to any variation. But in this case, they're not asking for the scale, and it's just an intermediate step that really is not required to answer the problem. Okay. So let's look at the next problem. Oh, that's not going to work because it's a blank page. So this is problem 75. This is a physics problem. Yeah, a lot of stuff in physics deals with things that are directly proportional. So, oh, there's somebody online. All right. So what we're talking about is if you, for example, where would this apply? Well, if you're swimming in a pool, the pressure at the bottom of the pool is greater than the pressure at the top of the pool because of the weight of the liquid above you. And you can calculate it easily. It turns out, from a physics standpoint, which you don't need to know to solve this problem, but I'm giving you a little extra insight for free. The difference in pressure between two levels is equal to the density of the fluid times the acceleration due to gravity times the height difference. So what they're saying is, they said that the pressure varies at a given point, varies directly as the depth. So this is the depth, and the other two things are constants: the density of the fluid and the acceleration due to gravity. The density of water is 1,000. Well, actually, it's in SI units, it's 1,000 kilograms per meter cubed. So if you take a meter, which is about this big, and you make a cube out of that, the water in that cube weighs almost a ton. 1,000 kilograms is 2.2 or 2,200 pounds. 2,000 pounds is a ton. So a ton of water. That's why you get a big, like a trash can of water. You can't lift it because it's just, you know, a trash can is probably not a meter cube. It's probably half a meter cube. It weighs a lot. Yes. Yeah, you need at least two people. Well, that's partially because if you lift it, you're bending over, whereas if you have two people, it's kind of balanced out as well. So there's probably two reasons. One is because you only have lifting half the weight, and secondly is that you're not having to bend over like this. You can stand like that and go. It's like those. You ever seen the things for moving furniture? It's like a strap that you put around your back, and and you'd have two people like that, and you clip it underneath the furniture somehow or another, and then you can just lift it up straight, because anytime you try to lift something with your back bent, especially as you get older, it's amazing how you can hurt yourself, hurt your back by just picking up something that you would not think is that hard. You know, just if I had my calculator on the floor, you're like, can I really hurt my back by picking my calculator up? The thing is, depending upon, you know, just exactly how you're aligned, you can hurt your back, and you're out of commission for like weeks. Okay, anyway, and the acceleration due to gravity is, depending upon the units, is like 9.8 meters per second squared. So anyway, there's a fair amount of this pressure difference between the top of a 10-foot pool and the bottom of the 10. I mean, you know, because if you've ever dived to the bottom of a pool, your ears feel the pressure. Yeah, it's not, especially when you're not used to it. I remember we went to went scuba, well, not scuba diving, that's too expensive, snorkeling in the Caribbean, and you know, you're like, oh yeah, I got my snorkel thing on, I'm going to dive under the water and be like you see on TV, and you get down about 10 feet and you're, the pressure on your ears is tremendous, especially, like I said, when you're not used to doing it that often. And it's amazing how buoyant you are when you try to go down like that. Anyway, so in this case, what it says is that the pressure varies directly. So if you see varies directly, you know you can just set it up as a ratio or as a proportion. And again, you can look at it two different ways. You've got three things here. You got two measurements of distance and one measurement of pressure. So we can set it up as a ratio where the length information is one proportion and the pressure information is the second proportion. And again, if you have 20 feet down here, you're going to have your answer here for 20 feet as far as the pressure. So we just have to match it up. So which way, where does the 50 pounds per square inch go in this proportion? Is it in the top or the bottom? By reading the problem. Which one does 50 match with? I know you know the answer, just nobody ever. That's why it's hard to get you guys to. You're always you're not very confident in your answers. But what? Yeah, it's in the numerator because it says at a depth of 10 feet, it's 50 pounds. So it's obvious that those should go together. So what you would do is you'd put 50 pounds, and we're going to use PSI as an abbreviation for pounds per square inch, and therefore the unknown goes in the denominator. And in this case, you could also do it with, you could do, 10 feet is to 50 pounds per square inch as something is to something. And again, here you would match up the units. So 10 feet, the feet units go on the top, and the unknown goes to the bottom. And in both cases, you can rearrange this. Now, the way I would do it, rather than cross-multiplying, I would say, I need to solve for x. That's in the denominator, which is the wrong place. So I'm going to move it to the left-hand side, and that means now it's in the numerator. I've got my 50 psi on my right-hand side, where I'm solving stuff. So if I want to move 10 to the other side, that's going to go to the denominator. And 20 is in the numerator, the denominator goes to the numerator. And so you do the math, you get 100 psi. The feet cancel out. And again, it makes sense because the greater depth you go, the higher the pressure is, the more the weight of the water above you is more. Now, have you ever heard about this? If you get below a certain depth, that you actually have negative buoyancy. So buoyancy is if you go in water and you just lay with your head down, part of you is going to be above the water. You're going to float. Now, normally the problem is that your nose is not above the water, so that's you might have to tread water a little bit. But if you have a snorkel mask on, you can just kind of lay there. You don't have to use any effort to float because you don't have to keep your head up to be able to breathe. You can just breathe through the snorkel. Yes. Oh, just float. Part of it has to do with how buoyant they are. Yeah, I would think because you're skinny. Yeah, so the reason. What's that? Yeah. Fat is not as dense as muscle, and therefore you float. Yeah, that's right. But skinny guys, you sink. So this is interesting. Has anybody ever been snorkeling at all? Okay, so snorkeling is fun because you don't have to worry about swimming. You don't have to, my wife always got freaked out about snorkeling because she felt like she had to be doing the normal thing where you're treading water, but you don't have to tread water. You can just kind of lay there. You just kind of fake like you're dead or something, and as long as you don't get water in your lungs, you're fine. So you can just relax and just float around, look at the little fish and the coral, and you can go a fair distance because you're just taking it so easy that you're not wearing yourself out. And she finally figured out that the last time we went, and she enjoyed it much more. Before, she was just get panicked about the whole thing. So what happens is when you go down in the water, the pressure on your body squeezes your body basically, and your volume of your body gets less, but your mass of your body stays the same. And as long as the density of your body, including the air in your lungs, is less than the density of water, you're going to float. But if you get down far enough, you get squeezed enough that your density is equal to, or actually less than, or equal to or greater than water, and at that point you don't float anymore. You don't have any buoyancy. Have you ever seen these guys who do these, what's it called, free diving? They go down and so once you get past a certain point, you're actually going to sink. So you don't have to work that hard to keep going down. The problem is getting back up because you're not going to float. So that's why you have the rope and you're pulling yourself up, or you're swimming. You're using you're propelling yourself to go upward, but it's not because you're floating, huh? Yeah, I hate flippers. So that's something. I use a snorkel mask and a thing, but I don't use flippers because I like to use like a frog kick. Anyway, that's a personal preference. But what can happen is if you're in like a helicopter crash, this is something they actually train for, is it's dark, you're in the water, you come out, you don't know which way is up because you're not going to float. You might be at a great enough depth that you no longer have buoyancy. So then sometimes people will swim the wrong direction. Of course, then you're dead. Okay, so the way that you do this, if I remember correctly, hopefully you can see a little bit, is you blow out some air, because the air is always going to float to the top no matter where you are. So you blow out a little air, see which way the bubbles are, and that's the way you head. Okay. Now, of course, if it was the first time that ever happened to you, you'd probably be panicking so much that you would never. Yeah, you'd blow out a lot. That, which also makes you less buoyant. Yeah, you lose your buoyancy when you blow out air, but knowing which direction to go is more important at that point than losing a little air out of your lungs, because you go the wrong direction, doesn't matter how much air you have in your lungs. Anyway, that's another interesting, useless fact. Actually, it's not that useless. It's like those car. You ever seen those? If you go into the water in a car, what you're supposed to do? Pardon me? No, you actually so here, what you do is if the car goes into the water, the first thing you should do, which is opposite of what you think you should do, is to roll down the windows. Okay? And then get the heck out of the car. Okay? A lot of people will have the windows up and they'll think, oh, I'll have this air pocket and I'll be okay. But the problem is that air pocket doesn't last very long, for one thing. Yeah, and then you can't open your door. The electronics don't work in the car, so you can't use your. Now, if you had the old cranking ones, you probably could open it with the standard, but the new ones have electric windows, so you. No, it won't come. You can't open it because the air pressure is pushing, the water pressure is pushing the door closed, but there's nothing. You can't push that. You can't provide enough force to open that door. So the only way you could get out is to roll down your windows, or to have one of those things that will shatter a glass. Well, there's actually a special tool that you can buy. What's that? Yeah, and it just shatters. Do you have one of those? Why do you have one of those? Okay. So yeah, so you can it's like in the lower corner of the window. It'll just shatter the whole glass, which is kind of cool. Anyway, this is survival 101. Yes.
You can buy pocket knives, and they have the little nozzle.
Oh, do they?
Have
you ever tried? That's another thing. You know, I'd like to do it one time, but then again, what do you go to the junkyard and shatter. It's kind of things that you would like to do, like if you're practicing to get out of a helicopter that's submerged. If you actually, in the Army, you'll train to do that. Oh, in a car? The newer, is that right? The newer cars actually have a release inside. Okay, back to math. I guess the final problem here is this one. So another physics thing is that the force required to stretch a spring is directly proportional to the amount the spring is stretched. So I just happen to have springs in here because it's a physics lab, and I'm the physics teacher. Well, good luck on your presentation there. So this is a spring. And the spring has what we would say is an unstretched length. So this is the unstretched length with there's no mass on it. And then if you attach a mass of some sort that has a weight, what will happen is the spring stretches. If I put two of these the same things on here, the spring will stretch twice as much. Which, I guess, can we show that is true? I don't know if we have enough room or not. Anyway, it does. The other way you could think about it, I've actually got something else in here. So even though you'd say, well, that's, it's kind of a simple relationship, does that really apply? And the answer is actually yes. This is probably one of the most important cases of a linear relationship. So this is a spring scale, and if I attach, which is actually a spring, and that reason it works is because of this phenomenon. But right now the spring's pretty light, so it reads pretty close to 0. If I were to stretch it this far, and I would get to the first mark, which is 5.5 newtons. If I stretched it so that I had 1 newton, the distance that the spring is stretched would be twice as long as at this distance. So the longer I stretch this thing, the more the displacement of the spring, the larger the force, and it's a linear relationship. It's directly the force that I'm measuring on this spring scale is directly proportional to the amount that this spring is stretched. There's a lot of things that relies upon. One of them is if I take this mass and I attach it to the spring, and there's some length where it doesn't stretch anymore. It's right there. Okay. Now if I take this mass and I move it from this point, which we call the point of equilibrium, and I let go, what's going to happen is this thing's going to bounce up and down. It's going to bounce up and down right through the equilibrium point, which is where it was when the weight of the object is the same as the spring force. And if I were to plot the position of this block as a function of time, it would be a sine wave. It would be a pure sine wave. And the reason it is because of the relationship between the force on the spring and the distance that you stretch it. If it's linear, it's an ideal spring where the distance stretched is proportional to the force, then this movement as it vibrates is a pure sine wave. So it's moving the fastest right in the middle. It has 0 speed at the ends. And there's a lot of things that behave like this that are not just obviously a spring with a mass on the end of it, but you know, anything that has some kind of springiness to it, like a car spring or an airplane wing or a bridge that is blown in the wind, can vibrate. And so anyway, that's my little physics lesson on springs today. In terms of this problem, the key thing is it says it's directly related, or what's the word they use? Varies directly. So varies directly means that it's just a proportion. And so the proportion is going to be inches to inches equals pounds to pounds, or inches to pounds equals inches to pounds, depending upon which way we want to do it. So we'll do them both ways. We'll set them up both ways. So we look at the problem. If a force of 12 pounds is required to compress a certain spring 3 inches, so we'd say 12 pounds is to 3 inches. So our proportion here is going to be pounds up here and inches down there. So it's easy to go back to the problem and see what else we're given. We're given 5 inches. So this is the unknown. What is the corresponding force at 5 inches? And again, you could solve for x. Well, to solve for x, all we have to do is get this term that's in the denominator and get it to the left-hand side, which means that the stuff on this side stays in the same relative location, and this 5, which is in the denominator, goes to the numerator. And then you multiply it out, you get 12 times 5 divided by 3 is 20. And again, the inches cancel out, and we get the units of pounds, which we knew anyway because we saw it in this point. Now, the other way you could do it is you could do inches to inches. So I could say, 3 inches is to 5 inches. And then when I make my second ratio, I put the corresponding pounds to whatever is over here. So 3 inches was 12 pounds, so I put that in the same relative position, which is in the numerator. And, you'd solve it and you get the same answer, 20 pounds. So that's all you have to do. Now there is an equation, force equals some constant times x. So that's also another way of saying that the force varies directly with the change in length. And you could solve for k. K is equal to F over x. So if I took my initial point, 12 pounds, where I have both pieces of information, 12 pounds divided by 3 inches, then I get 4 pounds per inch. That's kind of like, it's the conversion factor, or the proportionality constant that relates force to distance. Before we could have had, if we go back to the previous problem, when we were talking about pressure, it's actually, where did I write that? I thought I wrote it down somewhere. Where I was talking about the density and the acceleration. I didn't write it on the board here. I wonder where it went to. Anyway, I said the density times the acceleration due to gravity. That would be the proportionality constant. And in this case, the scale of the map would be the proportionality constant. But again, you don't need those in these problems because you can just treat it as a proportion. Or if you're doing we didn't actually do it here, but if you do cooking and you're trying to scale a recipe, say it feeds 12 people and you only want to do it where it feeds 6 people, you might have the recipe is 2 cups of flour and your original recipe is 1 cup of water. So you could, and you wanted to reduce this by a half, then you could use that proportion as well. That's kind of a, in that case, if you wanted to, you could base it on servings or something like that. So a lot of times cooking, you use ratios to change one recipe to another one. Like my bread recipe uses a teaspoon of salt for 1 loaf. It's going to be two teaspoons of salt for 2 loaves, 3 teaspoons for 3 loaves. It's just this direct proportionality. You want this ratio of the items to stay the same between the different constituents. So there's the homework assignment, which I gave you last time, so I don't need to do it anymore. So the last section we're going to talk about, which will be on the exam, but will not be on the final test, is properties of exponents and scientific notation. So what is an exponent, and what are the properties of exponents? So if you talk about an exponential expression, in this book it says that A is a real number, which just means it's a number that is not imaginary. So you could have A as a rational number, as an irrational number, pretty much any number that you can represent physically. N is a natural number. Natural numbers are 1, 2, 3, 4, 5, 6, 7, 8. Then the exponential expression A to the N is defined as just the base, which is A, multiplied by itself n times. So the number A is called the base, N is called the exponent. And there are certain rules that apply to simplify expressions that involve exponents. So these are the rules. So I'll explain, kind of explain how you get to these rules, and then you should be responsible for applying these rules for the exam. One of the things on the exam. So the product rule says if you have 2 numbers which have the same base, they're raised to an exponent. If you have a product of those 2 numbers, to get the final simplified expression, you add the exponents together. So here's our example. 3 is the base, 4 is the exponent. We multiply that by another number which has the same base raised to an exponent. It doesn't have to be the same. It can be different. It can be the same. And really what this means is 3 to the 4th power means 3 times 3 times 3 times 3. And 3 to the 5th power means 3 times 3 times 3 times 3 times 3. Obviously, we don't want to have to do that every time and say, well, okay, we have 4 3s and we have 5 3s, so I can write that as 3 to the 9th power. That would be the long way, which would be a waste of time. So what we do is we use the law of exponents, product rule for exponents, which says that all we have to do is add the exponents together. So the exponent here is 4 and 5, so you add those together and you get 9. And let me just close my mail here so it stops popping up. Now, M can be positive or negative, even though in the original expression, in the original definition of an exponential function, it said that the exponent had to be a natural number. So you think if it's a negative number, it's not the natural number anymore. But these rules apply whether the exponent is positive or negative. We'll see why they're negative in a minute, but for right now. But the only, when we ultimately evaluate this expression, and and come up with an actual number rather than the exponential abbreviation for it, the exponent has to be positive at that point. So we always want our final answer to be a positive exponent. But the intermediate steps can have a negative exponent. It's not the end of the world. So, you know, if I did this, what this represents is 3 to the 9th, and if I go to my calculator and I take 3 to the 9th, I'll get an answer which is 19,683. So that's just a compact way of representing that number. And why you said, why don't I just use the number? Because there are cases where, well, for one thing, it could be a lot simpler or shorter expression, more compact. And secondly, in terms of understanding the original meaning of this, the exponential form, instead of just the number form, provides insight. Okay, so that's the product rule. We have the quotient rule. So again, what in non-exponential form, let's just write this out. So the numerator 3 to the 4th, actually I didn't explain this. So the rule says if you have two numbers with the same base and they're exponential terms, the resulting exponential term when you divide them out is the exponent in the numerator minus the exponent in the denominator. So what's happening here is, say this example, 3 to the 4th is 3 times 3 times 3 times 3. 3 to the 5th is 3 times 3 times 3 times 3 times 3. And what happens is, you know, these cancel out because 3 divided by 3 is 1. Any number divided by itself is 1. And what we're left with in the numerator is 1, and what we're left in the denominator is 1/3. So that's the answer. What is it? What does this rule do for us? Well, pardon me? Yeah, you'll see that. Well, we have one additional rule here that will kind of relate these two. So if we just, instead of writing out it in its simplest form, we use the rule which says we still have the same base, that doesn't change, and we take the exponent in the numerator, we subtract the exponent in the denominator, and we end up with 3 to the minus 1 power. Now, one of the rules we haven't talked about yet is that if you have a negative exponent, you can make it into a positive exponent by moving it from the numerator to the denominator. So 3 to the negative 1 power is 1 over 3 to the first power. And 3 to the first power is just 3. So there's your final answer, same answer. In this case, I mean, maybe I should have chosen this to be larger than that, and then you wouldn't have this to worry about at this particular point. But that's a general rule. And you know, if I ask you to do this problem on a test, a lot of people sometimes just get to this point and they say, well, I applied the rule, I got the answer. But anytime, you should always look at your last answer, and you should never have a negative exponent in your final answer. You should always move anything that's has a negative exponent to the other part of the fraction and make it positive. You can just go directly from here to here. Yeah. The reason I included it is because, you know, if I didn't show it, then you'd say, well, this is more obvious that I'm changing the sign, but then I drop it. But if you know that 3 to the negative, that's the only one it works for, is when it's just to the single negative power. Okay, then we have the power rule. So there are a couple of them here, depending upon how you have it set up. Basically what we're doing is we're saying we have an exponential function that itself is raised to a power. So let me just write it out and explain what's happening here. So 3 squared is 3 times 3 because I have the exponent is 2. So that means I multiply 3 by itself twice. I guess by itself once, but you have 2 3s. I'm going to leave the parentheses here, and I raise that to the 3rd power. So if I multiply this out, I'd get 9 to the 3rd power. And if I take 9 to the 3rd power, I get 729. But you would find out that that is also 3 raised to the 6th power. If I take 3 to the 6th power, I'll get 729. So what I have here, to get to the 6th power, you see that if I added the exponents, I'd be wrong, because you'd have 2 plus 3 is 5. So you end up having to multiply this number. If you did this example with, choose some different numbers, you'd find out by inductive reasoning that you see this pattern, and you see that the final value here is always the original base to the exponent where you multiply these 2 exponents together. So that's kind of the way I would explain it. You get a final number and then realize, oh, I can do 3 to the 6th power, which is my original base. Here I have kind of an intermediate base. So that's the first example. So instead of doing it this way, I would just say, well, 3 to the 2nd power, or 3 squared cubed, is just 3 to the power of 2 times 3. 2 times 3 is 6, and I get the answer. And then I could use my calculator to do that, or I could take 3 times 3 times 3 times 3, whatever. Now if you have a product inside a parentheses raised to a power, then that means each term in the parentheses is raised to that power individually. So let's look at an example of that. So if I had 4 times a raised to the 2nd power, that's equal to 4 to the 2nd power times a to the 2nd power. And I wouldn't normally leave that as 4 squared. I'd go ahead and multiply it out. So I'd have 16a squared. Okay, so let's do another one. If you do a times x cubed, that's going to be a cubed times x cubed. And again, it makes sense. Let's just write this out in the long form. What we have is a times x cubed. So you have a times x times a times x times a times x. That's what a x cubed is. And this is really a times x times a times x times a times x. So that's a times a times a times x times x. Doesn't matter when you have multiplication. It doesn't matter which order you multiply them together. So I can move these around any way I want, and I'm going to put all the a's in the front, and I'm going to put all the x's at the end. And then you can see that I can then write those in exponential notation as a shortcut. So I have a to the 3rd power times x to the 3rd power. So that's that rule. That's why the rule works. And then the final one is if you have a ratio, so let's say you have 2/5 squared, that's the same as 2 squared divided by 5 squared, which is going to be 4 divided by 25. Because, 2/5 squared is just 2/5 times 2/5, and when you multiply rational numbers together, you multiply the numerators together and the denominators together, and you get the same answer. So this is using the law of exponents. This is just using the definition of an exponential function where the argument is a fraction, which is fine because the only requirement said was that this is a real number, which this is a real number. So anything. Okay, we got a few other little laws here. A If a is any non-zero real number, then a to the 0 equals 1. So if you take 2 to the 0 is 1, pardon me? Yes. So, yeah, so 0 to the 0 is 1. 1 million to the 0 is 1. A to the 0 is 1, or B to the 0 is anything. Doesn't matter. Chicken to the 0 is 1. So it doesn't matter what it is. And you're like, how does that make any sense? Because, yeah, 0, well, for one thing, if I go back, I just thought about this. If you go back to my original expression here, or initial definition, it says n is a natural number. Well, 0 is not a natural number. So what does that mean? Why did that work? Or why does that? It's kind of like the question of why can you have an exponent other than natural numbers? And the answer is yes. If you plug into your calculator, it'll still give you an answer. 2 to the 2.5 power is something. It's not undefined. So let me give my little explanation here of why you can raise, even though the original thing said only to use what do they call natural number. If I plot, use an arrow on both sides here. So let's pick, this is going to be x versus y, and y is equal to x to the, what letter did they use back here? I think it was n in the original definition. N, yeah, okay, x to the n. So this is 1, this is 2, this is 3, this is 4. So, and we'll do 1, 2, 3, 4, 5, 6, 7, 8. Okay. So when, let me just draw a table up. When x, and we'll do it to the second power. So I'm going to use specific value of n. Yeah, actually so this is y, which is equal to x squared. So if you have x equal to 1, then 1 squared is 1. If you have x equal to 2, you have 4. If you have x equal to 3, you have 8. And actually, because of the definition, I am using a whole number, a natural number, so that I can use any value of x. I'm explaining why 0, why when you, am I doing something wrong? I'm doing something wrong here. What am I doing? No, this is the other way around. I want the base to be 2. Yeah, 2 to the x power. That's what it is. Let's try this again. So this is y, which is 2 to the x. So when x equals 1, it's 2 to the first power, which is 2. So that's that point. I've got 2 squared, which is 2 times 2, which is 4. So that point is right there. So it's 2 comma 4. When x equals 3, you get 2 times 2 times 2, which is 8. So we plot that at 8. Okay, so that's good. So what I'm doing right now is I'm limiting myself to natural number exponents. Now, what happens if I let x equals -1 and -2 and -3 on the other side? So y is, again, 2 to the x, so it's going to be equal to 2 to the -1, but we have this new rule that says 2 to the -1 is 1 over 2 to the first power, which is equal to half. So I can plot that. So if I go on the negative side, -1 I get a half. When I have 2 to the -2 power, that's really 1 over 2 squared, which is 1/4. So I can plot 1/4. And if I do 2 to the -3 power, that's 1 over 2 cubed, which is 1 over 8. And so the question is, why was I able to do this? Well, because when I finally evaluated this exponential expression, it was when the exponent was a positive integer. So I didn't evaluate it. It didn't say 2 to the -1 is a half. I said 2 to the -1 is 1 over 2 to the first power, which is 2 to the first power is 2, and then I get that answer. So those, even though the initial exponent is not a natural number, by converting it to this, it is a natural number, and therefore I can assign a value to it. So if you were looking at this and figuring out if you drew a line through these points that I can use the original definition of a exponential function, so this is going to be an 8, what would happen is it would look like it approximately goes through 1. I mean, you wouldn't know exactly, but it has to be close to 1. So that's not surprising that any number raised to the 0 power is 1, because on one side it's less than 1, on the other side it's greater than 1, and with a little curvature to it, it's going to go through 1. So that would be my guess. And so the second question would be, can I have exponents that are something other than an integer or a natural number? Good, because if I could, then I could just start getting points closer and closer to 0, but not actually equal to 0, and I could plot those points. So let's just talk about the question of, how do you handle non-integer exponents? So let's say I have 2 to the 2.5 power. So how do you, if you take the original idea of exponential stuff, you know that 2 squared is equal to 2 times 2, and 2 cubed is equal to 2 times 2 times 2. So 2 to the 2 point, it's equal to the, that's half of a 2. What do you do? What do you do with that half? So the way you do it is, that 2 to the 2.5 power is equal to 2 to the second power times 2 to the 0.5 power. So this part I can evaluate because it's a natural number, 2 times 2. The question is, how do you deal with a fraction? So the way you deal with it is you would actually make it into a fraction. So it's going to be a half. And it turns out when you have a fractional exponent, that is equal to the root, in this case the second root of the value of 2. So we're kind of going to a different concept here. We're not using the exponential thing. We're looking at what that means. And what that says is what number multiplied by itself twice equals 2. We usually don't show the 2. We just leave it off and call it the square root. But the way you would figure this out is you pick a value of x, and then you'd look at x squared. So 1 squared would be 1. 1.1 squared, you can do that calculation in your calculator. 1.1 times 1.1 is 1.21. 1.2 squared is multiplied by itself is 1.44. 1.3 squared is 1.69. 1.4 squared, which I'm just using the definition of exponential. I mean, I have the base can be a non-whole number. In this case, the or non-natural number. In this case, if the exponent is a natural, the base is non-natural. It's just a real number, but the exponent is a natural number. So I get 1.96. If I tried 1.5, I get 2.25. So, you know, the value of x, when multiplied by itself, that gives a value of 2 is going to be somewhere between 1.4 and 1.5. And you could keep, then you could say, okay, I'll try 1.41, see where that is. You know, and you could keep, by trial and error, you could come up with the value of x such that x squared equals 2. Well, your calculator does that for you if you went through the long, laborious process of doing that. But if I just take the square root of 2, I find out that 2 to the 1/2 power is 1.41421356.2. Okay. And so at that point, I can just multiply everything out again. So I take 2 times 2 times 1.41421356.2, and I get 5.6568, etc., etc. So 2 to the 2.5 power is this. So it's doable. You just have to deal with this non-integer part of the original exponential expression by it ends up being related to a nth root, in this case the second root of that same base. And there are ways to get that number, and then you just multiply them together and get the final answer. So if I plug 2 to the 2.5 power in my calculator, I should get 5.6568. 2 to the 2.5 power, which is 2.6568. Okay. So now that I've figured out a way of dealing with non-integer or non-natural number exponents, I could try exponents closer and closer to the to 0. And you would see on the left-hand side they approach 0. I mean, approach 1. On the right-hand side they approach 1. And you can make the conclusion that any number raised to the 0 power is 1. That's kind of a long explanation. You probably just like, why don't you just let me accept that's the truth? But so that's where that all comes from. At least that's my interpretation. I've never actually looked in the book how they explain it, but that's the way I would explain it. And then the final one that we've already used is that if you have an exponential expression where you're raising to a negative power of n, where n is a natural number, but it really doesn't have, it could be a non-natural number. You can rewrite it as 1 divided by the same exponential expression, but with the exponent changed from minus to plus. And you can use those rules to simplify and evaluate exponential expressions. So that's what we're going to do here. The first couple, these are examples like the ones for homework. In this case, you know, you might just stick it in your calculator, but what they really want you to do is just to show what it means. So 10 to the 3rd power means 10 times 10 times 10. There's no way I could tell that you didn't do it the cheating way on the calculator unless I asked you to write it out, which I probably would. So when I show you something like this, I want you to write it out and then pretend like you're using your calculator to do 10 times 10 times 10. Okay, so that's easy. Now this is a real sticky point. People get this wrong, and I try each year to do a better job of explaining it. When you have a negative in front of a base, because you can have positive or negative bases. Doesn't have to be, it said it just has to be a real number. And real numbers are negative as well as positive. The key thing here is there's two ways of writing this which give you different results because they mean different things. But so when you do not have a negative sign inside parentheses, what this is not negative 2 times negative 2 times negative 2. It's negative the quantity 2 times 2 times 2. So we don't do this operation, we don't include this operation in the exponential unless it's inside the parentheses. So this is, you do the cubing first, which means I'm going to cube 2 times 2 times 2, and I'm going to take the negative of that. So the answer is negative 8. Now you actually get the same answer whether you do it this way or this way in this particular case. What we have here is you have negative 2 cubed, so you take negative 2 times negative 2 times negative 2. And that's still equal to negative 8, because you have 2 times 2 times 2, which is 8, and you have an odd number of negative signs, which means it's negative. Yes? That's what we're going to do next. Yeah, so let's look at that. Let's say we... Okay, so let's say we have this expression. We have two ways of doing it. If your exponent is even, you're going to get different signs. If the exponent is odd, you get the same sign in the answer. So what this is, and this is what I expect you to do on the test, if I give you this, I don't want you to go into your calculator and go negative 3 to the 4th. You get an answer. What I expect is you to write this out, what this really means, which is negative 3 times 3 times 3 times 3, because we do the exponential first in this case, and then we take the negative of that. So 3 times 3 times 3 times 3 is 81, and then we take the negative of that. Whereas in this case, you have negative 3 times negative 3 times negative 3 times negative 3. So 3 times 3 times 3 times 3 is still 81, but a negative times a negative is a positive, and a negative times a negative is a positive, so this ends up being positive 81. Okay, so what you would, if you were verbally describing this, because if I said, what's the difference between negative 3 to the 4th power and negative 3 to the 4th power, you would know that it was different. You can see it visually. What you do is you would say, negative 3, the quantity, to the 4th. You add the quantity, so that it knows that negative 3 is the thing that you are doing it. But in this case, you would just say negative, this would be negative 3 to the 4th. You could say the negative of 3 to the 4th. Yeah, but you probably just would say negative 3 to the 4th, whereas the second one, you put the parentheses, you always say the quantity. So for example, back to algebra, if you had x plus 1 squared, what I just said was actually x plus 1 squared. But what I would say, so that's not correct, that's not what that is. I would say the quantity x plus 1 squared. So it's always, verbally you have to put that, the quantity, which is basically putting parentheses around it. So that's how you know. But sometimes people get lazy and they would just say negative 3 to the 4th power. But they should say the quantity negative 3 to the 4th power. But here it's obvious, which it should be obvious. Okay. So the answer is going to be either positive 25 or negative 25. So we'll do a vote here. So give it a thought. Just make sure you just do the order of operations. Parentheses. So you would do everything in the parentheses. Well, that's already done. Exponential. So you do the exponential part next. And then you would do, the last thing is you would change the sign of the result. So how many people vote for positive 25? How many people vote for negative 25? Okay, so that's good. So what you end up with, what you're doing here is you're taking negative 5 times negative 5. So this part is this part right there. That's -5 squared, which -5 times -5 is positive 25, and then you change the sign to make to negative, so it's negative 25. Okay. Now this one again is you're doing this first, which we can't do anything with that until we rewrite it with a positive exponent. So this negative sign is the same negative sign here. But then when you have a negative exponent, first thing you do is you write it as a positive exponent in the other. So if you had something like 1 over 7 to the -2 power, what would that be equal to? Yeah, so you can do the same thing in the other direction. So if I have a negative in the denominator, I can move it to the numerator and make it positive. So this is 49. Now over here, it's going to be equal to -1 over 49. So the original one shows a negative exponent in the numerator, making it positive in the denominator, but the exact opposite is true. If you have a negative exponent in the denominator, you just move it to the numerator and make it positive. So if I had something like a to the -2 power times b to the -3 power divided by c to the -4 power and d to the -1 power, so they're all negative, that's equal to c to the 4th power, d to the 1st power, divided by a to the 2nd power, and b to the 3rd power. So all I did is move these to the denominator, these to the numerator, and they became positive. So I'm going to assign the homework, because this will be due next Friday. So let me give you we'll do more of this Thursday. Actually, what I'm going to do is, because we didn't get far enough to do enough examples, this will be due at the exam. Okay. But if you want to start working on it now, you have the assignment. I might not even have any chance to talk about Chapter 8, which is fine. That's why I ended up changing the order, because I wanted to have a chance to talk about new stuff instead of old stuff. So if I ran out of time, I'd rather what? Yeah, it's kind of like graphs, linear graphs and stuff like that. So anyway, so we will see you next Tuesday for the test. Can I like the imaginary number? Yes. Yeah, that's a complicated question, because yes, there are, especially in higher level math. Here's one of the interesting e to the I times theta is, no, actually it's e to the I times pi is equal to -1. And it takes a little while to explain that. But so yes, there's an example of where you have an imaginary exponent. And I'll give you my 2-minute explanation, is you find out that e to the I times some value, like an angle, is equal to the cosine of theta plus I times the sine of theta. So when you have an imaginary exponent like that, and typically it only happens with e, there's this relationship between e and trig functions. So it's a linking mechanism. Why that's true, you have to know about infinite series, which is in the second part of the second semester of calculus. Yeah, let me,